So, yes, Simon.
Yeah, really interesting talk. Given that in today's systems we burn a lot of power moving data, around the chip, and in particular on and off chip. Often when people talk about energy efficient compute, they immediately start talking about energy efficient computation. But should we really be focusing on computation, or should we be focusing on communication? After all, if you look at mammalian brains, one of the key ways a mammalian brain saves power is using adiabatic communication processes.
I certainly agree, but Antonino, do you want to share your thoughts?
Well, definitely, optimizing communication is one of the important part of this. When we build a data path in an accelerator, it's a data path, right? we are trying to move data, not the computation per se. Or chiplet-based system, like in-memory computing, right? I was making the example for HDC. Your memory will become the computational element, but how you are going to build this system, right? That's what we are trying today to address with DeCoDe. There's obviously other initiatives where we are thinking much more about in-memory computing at large scale, right? Our Amaze project with Micron, where they're we are really thinking about disaggregated memory where you can operate near the memory in your CXL domain, right? And one possible application of a chiplet system like this is to prototype this near memory accelerator that you will put on your CXL card, right? And perform the operations there, data compression, for example, or data filtering at the beginning, so that reduce much more the power cost of moving the data, right? So
Simon, I would add a couple of other things that I focused a lot on, composable heterogeneous computing from a hardware perspective and from a system software perspective. Antonino mentioned this as well, though. There's actually memory support for heterogeneous computing. One of the most wasteful things to do is probably have separate memory pools for each processor types. And so while CXL may not be the end protocol that we need to use, we need something like CXL for shared memory pools so that can support and enable heterogeneous computing. That also drives a lot of energy efficiency benefits. The other thing I forgot to mention was that when we started this project, our vision was that the long-term goal would be a development of advanced architecture concepts that might have a chance of being deployed in a future leadership computer system, a future supercomputer. It's certainly not 5 years out, probably longer, but the goal for hardware prototyping would be to develop a proof of concept prototype that actually could show the benefit of running real applications on real hardware, albeit prototype hardware, but you could get real performance data. You could run our real applications rather than simplified applications that you often have to cut corners if you're using simulators or emulators. You could measure an instrument and measure real power consumption and energy usage. So that's one goal that still holds. But since we submitted this project and it was awarded, we come to realize there's actually a whole other use case that has been mentioned here, and that it has to do with edge computing. Now, there are a lot of edge computing applications and use cases where the processors from NVIDIA will be just fine, or Arduino or other very more simplified processors, but there may be a number of users in the DOE experimental ecosystem where edge processing that will push the performance limits or the energy efficient computing limits may actually benefit from customized hardware design and heterogeneous computing. They may not ever receive or achieve the volumes of production that make it reasonable to use commercial EDA tools. And so that's another use case that we're starting to look at very seriously as, we'll call it low volume, but maybe production grade processing and computing.
Hello? So you are not challenging TSMC or SML?
No. And also we're not challenging Synopsys or Cadence either. The fact is, what we're trying to do is open up this R&D space. You know, the goal of the CHIPS Act is to cross the valley of death. But our supposition is you shouldn't do that in one giant leap. You should do that by having intermediate steps where you can do hardware prototyping of maybe a dozen design points, and then use that to inform make an informed decision on what are the best optimal designs to invest in non-recurring engineering and converting an advanced concept to a product.
Add that, like hardware design tools, open source, I've always, at least since I was a student, right, great research tool. My PhD thesis is based on that. What DeCoDe is trying to do is what Jim is saying. Like, can this open source community converge and get that next step, right, that will enable us to actually do prototyping, so more solid than, like, research is great, but like your research needs to become applied, right? And that's basically the idea of DeCoDe, crossing the valley of death between lab-to-fab.
So, yes, Kevin.
Right. Nice.
Yes. So not in the space of microarchitectures, bear with me. I'm thinking of processors and, you know, our computing elements that we want to use. We had these hard-baked things that are taped out by Intel and so on, and they didn't really suit everyone's needs. Then there are FPGAs where you could go in and, you know, lay out exactly what you want on it. And if I understand this project, or at least the direction we're going at here, is more of helping folks to design more in this, or to make better designs in this, you know, hard-baked solutions area. But we still have this reconfigurable, let me build it for whatever I want now. Do you see us getting to a point in the same way we have 3D printers now, where you can go home and print your own little rubber boat or your vase or something to stick on your printer? Getting to that point where folks will be printing their own processors in a more, let's say, cost-effective way than what we have now.
I guess I would say that it may be within reach for a number of the analog accelerator concepts, where, you know, state-of-the-art technology nodes are actually not very effective in analog computing. But I don't know that we'll ever get down to printing at 2 nanometers. But then a company like Canon is trying to compete with ASML. So I'm not sure what their solution is, quite frankly. Antonino?
Yeah, well, I would say not print at home, but definitely like enabling you to do your own hardware design. Basically, like, didn't explain too much, but some of these chiplet, once you have the standard, can be FPGA, for example, right? Then, like, if we get the opportunity to get some of these designs actually implemented because it's all standard, right? You'll put an FPGA with your own design. Even more, we have use case that Jim was highlighting, where the small prototype moving to production, SODA is perfect to do that. Was designed. The dark path was actually excited to do that for autonomous control, where, like, also you don't think anymore, oh, I have a memory, I have my inference engine that is just a throughput engine. Nothing. Like, your focus is low latency, right? can an FPGA do that? Yeah, so sure. Like you can put an FPGA, but if I have the possibility to move to an ASIC or to a chiplet-based system, it's going to be much more efficient than an FPGA, because like you may just need a few functions, right? And you don't need the power to reconfigure. But like the tools enable you to do all this type of design, right? And democratize the design part. Then, sure, maybe it's not yet print at home, but like if you find somebody that supports you to go to a tape out or MPW shuttles, right? That maybe the government can support at that point, because like there's a cost, but hopefully we have enough production capability, then sure, why not? You shouldn't be able to
Yeah, maybe it's like design at home, but go down to the 1 hour photo for printing.
Yeah.
Sounds good.
David.
There's a couple of interesting companies like Atlan 3D who are doing essentially a 1 micron inkjet printer. So you basically have a little, you have your vapor deposition chamber with whatever material you want, and it's basically depositing it, and you trace what you want. So you wouldn't necessarily use it for a full complex circuit like this, but it could be the kind of thing you could use to do exotic materials testing and testing out new, interesting nonlinear transistors or analog components. Is that the sort of thing that would be of interest in this community as well, do you think?
I think so, just because PNL has other two MSRC projects, and are mostly focused on the material side. Actually, the other one that is collaborating with us is looking at a new type of resource, right? So
yeah, I mean, it just seems like it would be the sort of, you could experiment on the small scale, fabricating things that you don't want to yet invest trying to make a full, VLSI design with. So
yeah, I think some of this is in the co-design project, the BISCO that Jeff Vetter talked about. Actually look at advanced material devices, designs that actually get implemented as devices, fabricated specialized devices. Then you climb the curve with circuit architectures, create multiple devices into type of an accelerator. Yeah. These, I'll say, the cost is often a driver of invention. Like we just saw that with DeepSeek, and we'll see that with nuclear power reactors. Although Oak Ridge is perfectly happy to have more small nuclear power reactors, but when the cost of computing is so high, then there will be innovation. It'll drive innovation. The cost of ASML machines is so high that it probably is going to drive new innovation. I would not be surprised if in 5 years there's competition. So,
join me saying thank you to Jim and Antonino. Please.
all right. Well done.